I'm Ben. I lead the go-to-market team with Wherobots. Been with the company for a couple of years, and I'm personally really excited about just how fast we are shipping these days. It's crazy. Um, in terms of new capabilities coming out. We're going to be talking a lot about RasterFlow today. RasterFlow is our latest sort of perception and inference engine for handling and processing data about the physical world and the Earth. Um, and we've got Isaac Corley. Isaac, you want to say hi to the folks?
Yes. Hey, everyone. I'm a senior ML engineer, one of the creators of RasterFlow. So happy to be sharing all the cool stuff that we're building with you all. Thanks for joining.
And Isaac, your mic is a little faint. I don't know if you can turn it up just a little bit, but
Oh, yeah. Can you hear me now?
that's a little bit better. Yeah, awesome. And then Phil, you go ahead.
Yeah, hi everyone. Phil Deringer here in the product management team at Wherobots, working on RasterFlow, working with Isaac to launch and bring out this product.
Awesome. So we're going to be, like I said, talking about getting started with RasterFlow, and in particular, really, showcasing how you could quickly move past a lot of the challenges with image prep when you're working with RasterFlow. That's one of our biggest goals with building it, is making it so that you're able to handle um, imagery and overhead data with ease, so that you can really get to the insights that ultimately you want when you're acquiring uh, imagery data sets. But before we get into that, I'm just going to give you a little bit of an update on Wherobots and how we are continuing to innovate with data about the physical world. And I want to start with just like how we think about things from a company perspective. So, if you think about the last 20 years up to like around early 2020s, everything that we did was really around digitizing intent and behavior about what people were interested in, what they were searching for, what they were interested in buying. Um, and these are what we would consider to be traditional data and AI workloads. Um, Obviously today, I'm having a bit of a moment myself about like how quickly we are doing things differently, especially in an agent first world. But increasingly, we're really focusing on, and the customers that we were working with are really focusing on digitizing reality. And that's because there's just so much, need for understanding the physical world, whether that's mobility as a service. I just got a new car last week. It's a new electric vehicle. Um, it navigates itself. If I put it in self-driving mode, it will drive me, on the freeway in particular, it will change lanes for me. It's, a completely new paradigm for how we move around. You can hail a Waymo in San Francisco or elsewhere, a number of cities now increasingly all the time, and it'll come right to you. Robotics is continuing to grow and take control of how we do things. And increasingly, we're hearing about world models. I think if you're following Yanlin Sun, who was used to be at Meta, just raised like $1 billion for his world model startup. So anyway, there's the physical world continues to be a focus as we move into this world of interactive experiences that are changing. But the thing that we continue to see, and what we really focus on here at Whereabouts is the talent gap. There's a lot of developers that are out there building really cool stuff, but the amount of spatial data software developers that are familiar with things like, image preparation, coordinate reference systems, and handling data about the Earth are really limited. And this is a gap that is preventing us from taking advantage of the needs of the physical world, data and AI faster. And that's also sort of compounded by the fact that general infrastructure makes spatial data engineering really cost prohibitive. There's a bunch of traditional solutions that are really powerful, but once you hit a certain scale, they don't work anymore. Think about like PostGIS, GeoPandas, or your traditional GIS systems. Um, Modern cloud engines like Databricks and Snowflake, while they're really powerful, they only support a small portion of the overall types of geospatial functions that you need in order to handle and answer questions about the physical world. And then lastly, LLMs and code gen systems oftentimes are not really skilled in spatial data. They'll lack the knowledge of spatial functions and fine-tuned experience and skills, as well as the ability to interpret the data sets that they have at their fingertips. So at Wherobots, we're really focused on delivering on this developer platform for physical world AI, making it possible to take advantage of coding assistants that have understanding about what and how things work in the physical world. Our teams are shipping faster consistently. We just released our new agentic sort of experience within VS Code. So if you go to VS Code and the code extensions available there, then you can get started and try those out. I'll share a link here in just a minute. That pulls directly from the Wherobots global hub. So when you're inside of Wherobots or you're using your favorite code agent, you can interpret and determine, what models, what data, what notebooks, and also you can create jobs, you can create runbooks for your data, and really ship many times faster with these types of physical world data products. That then calls to Wherobots RasterFlow, which we're really going to dive deeper in today for these types of computer vision and perception type workflows. And then also can call and talk to WherobotsDB on back of the RasterFlow processing to do additional joins, do additional data cleanup, and then ultimately make your data ready for your end user experience. So when we're talking about what we mean by this developer platform for physical world AI, we really are focused on creating a lakehouse architecture where you're able to connect to your data where it sits, whether it's in AWS and S3 and blob storage, or in other lakehouse or warehouse systems. You can connect directly to Databricks. You can connect directly to the AWS Glue catalog or your catalogs of choice. You can connect to your imagery. You can join that with streets or buildings or other physical world data assets. And then you can really build and iterate in an agentic way. So you can have your agent discover what's in your catalog, identify what you want to build, plan, and build those things, automate, and then ultimately produce your end user facing application. So I'm going to pass it over to Phil to talk a little bit more about RasterFlow and what we're doing with Wherobots RasterFlow.
All right, thanks, Ben. Yeah, as Ben mentioned, Wherobots RasterFlow is a relatively new set of capabilities we first launched in December. It's currently in private preview, but we're working with a number of clients, both big and small profile teams that are using RasterFlow to generate insights at global scale faster and cheaper than they were previously able to do. So RasterFlow is fundamentally a new engine that we've developed that's optimized for the type of processing you need to do on aerial imagery, satellite imagery, to efficiently transform that data, prepare it for inference and analysis, and then be able to apply computer vision models and run those models at scale. As much as possible, we're building in years of collective expertise, both from people like Isaac within our team and the collective knowledge of the community, to make this easier for people who are relatively new to this. So trying out Earth observation for the first time, how can we make it as easy as possible for new users to get insights from this type of imagery as quickly as possible, while still providing knobs and controls for the more expert users to really fine-tune the performance of these pipelines. As with the rest of the Wherobots platform, everything we do is on demand. You pay for only what you use. And we'll be sharing shortly our price points. We're currently in private preview and finalizing our pricing, but we're very excited about the price points we're able to achieve for both smaller scale and larger scale analysis. And last but not least, it's fully integrated with the rest of the capabilities we have in Wherobots. With WherobotsDB, all powered by Apache Sedona, you have the tools right there to be able to post-process these insights that you're generating from these pipelines and really make them usable within your business context. So that could be cleaning up some of the geometries that are predicted by these models, or joining these data sets with other business contexts, other spatial data sets that you might already have within your lakehouse architecture, so that you can really drive operational change within your business. Just a high-level overview of how the building blocks of Wherobots RasterFlow. On the left-hand side, we have, for our models and data sets, we have a combination where we pre-populate certain models that we've chosen from the industry, open models that you can run, or open data sets that you can get started with right away. So for instance, on the model side, we're working actively, Isaac's the active leader of the Torch Geo community, and we're working with that team and that community to build and bring models that are relevant for our use cases into the platform and make it easy for any Torch Geo model to be used within RasterFlow. But you can also bring your own model. So anything, if you have your own model, computer vision model that you've trained with PyTorch, the simple process to export that model in the PT2 archive format and then register with the platform for use within Inference. Similarly, on the dataset side, we're populating this with open datasets that are available in AWS, starting with Sentinel-2 and the high-resolution dataset for the US from called NAIP. Those are the initial datasets we have in private preview, and we'll be building those out as we get towards public preview and GA and adding more datasets there as well. But similarly, we have a pathway for if you have your own imagery data you've acquired yourself from commercial providers, or your own drone capture, for instance, there's a process for bringing those in the form of COGS or cloud optimized GeoTIFFs to the platform so you can run the same pipelines against that data. And then you have these building blocks so that you can help ingest and prepare that raster imagery for inference. So we have building blocks to manage all the ingestion for the chosen area of interest, your AOI, build composites as needed if you want to build a composite or an average representative scene over a specific time range or an annual view of that area, and handling mosaicing as needed. So stitching together imagery to create a nice, clean, inference-ready mosaic, handling things like cloud cover so that you get good, clean inputs that you can use for inference. And then that would be the next building block. So we have a dedicated inference engine that we've built up to take those input mosaics, run your chosen model, either, again, a curated model that we provide or one of your own that you brought to the platform, and efficiently, at scale, in a massively parallel operation, run that model across that mosaic in a windowing operation so you get nice, clean outputs as outputs for that model. We help to eliminate edge effects that you might get if you just try and run that model tile by tile against the imagery, and instead you get a nice, clean output mosaic as the output of that stage. And then you can use additional tools within RasterFlow and WherobotsDB to work with those outputs. You can first call another workflow to vectorize those, to convert those initial predictions. For instance, in this case, we're seeing small screenshots of a model that predicts where sidewalks might be in urban environments. So trying to see where sidewalks are, we then take those predictions and the confidence levels that are expressed in that raster imagery or that raster output, and we can convert it to vector geometries that you can then post-process or simplify to make, for instance, in this case, a map of walking infrastructure or pedestrian infrastructure in a campus environment. And that's where the power of WherobotsDB comes in to do that post-processing, do any joins that's necessary, ultimately help you produce and build a map, either a map data product or a visual map that you can use in your applications. Yeah, last webinar, we talked a bit about in detail about how we're working together with the tailored geospatial engine, specifically around a model called Fields of the World. So Isaac's been very involved in this effort to build a global model for predicting field boundaries, agricultural field boundaries around the world. So the team there, tailored geospatial engine, with Isaac's help and others, have been developing further evolved generations of this model to provide better performance that works better across larger geographies. This model basically takes in Sentinel-2 imagery and predicts where the fields are, what constitutes a field, or what is a non-field or other type of area. So we work together with tailored geospatial engine, provide them with the engine where they can efficiently run this at scale. And there was a previous blog post back in the end of November, we talking about how the fact that we could now run this very cost effectively on new regions. And we quickly did Japan, Mexico, and a handful of other countries for them so they could start to see the results. How is this model actually holding up and performing in other geographies where they might not have had initial training data or labeled data? And stay tuned. We're about to announce further collaboration we've done with Tera Geospatial Engine to do a full worldwide run of this model. And we'll have some exciting results to share there very shortly. So that was Fields of the World. If you go to the next slide and just cover a quick breakdown of how that actually worked and how a model like Fields of the World runs within RasterFlow. So it starts with the source imagery. Here in this case, we're working with Sentinel-2 imagery already in AWS in the form of cloud-optimized geotiffs sitting in an AWS S3 bucket. And within RasterFlow, you can we've set up for these built-in models, we've set up these high-level recipes that orchestrates all of these steps of these workflow, including sourcing that initial imagery from AWS and S3 for your chosen AOI, then picking out the tiles that are needed for your area and your time range of interest. And in this case, we're building a mosaic composed of the planting and harvest seasons for that area. The model in this case is using those two different time ranges to try and see the differences and then better predict where the actual field boundaries are. But again, we're orchestrating all that, creating those cloud-free mosaics for those two different time ranges, backing that together as an input then to the Fields of the World model. Then we run that model at scale across your chosen AOI to generate these raster outputs. You would see these are pixel values representing the confidence level of a field or a field boundary across that AOI, initially in the form of raster. And then you would do a next step if you want to convert those, if those results look good and you want to convert those to vector geometries, that's just one more step in the workflow to vectorize those. And then you have basically tabular geometries that you can work with within WherobotsDB using the power of Apache Sedona and other frameworks to help post-process, clean up those geometries, create calculations, for instance, around NDVI per field. All of that's possible once you have those vectorized field geometries and the power of WherobotsDB. So that was the use case we showed last time with Fields of the World. Today, we're going to show another model that we have support for within the private preview of RasterFlow. It's a Canopy height model developed by Meta and the World Resources Institute. So this model has been trained on imagery worldwide and including LiDAR data to help estimate tree height, canopy height. But here in this case, we're feeding it high resolution data coming from NAIP for the US, and then using it to calculate the estimated canopy height or the tree height for any given pixel, right? For any given point in your AOI. So Isaac's going to walk through here a more detailed example we have that's using that, not just running the model once, but running it twice so that we can do change detection. Let's see if we can find out areas that have changed over time. That might be deforestation, it might be tree growth, and we can look at those two different time ranges to see how things have developed. So similar flow here, a little simpler in some ways than the previous flow with Fields of the World, but again, we're going to the NAIP imagery, which is already loaded into an S3 bucket in our chosen region. And in this case, we're orchestrating two separate workflows that are going to grab two different NAIP time ranges. So NAIP for 1 year and NAIP for another year to build two different mosaics. We're going to run that twice, run the model each time against each of those annual data sets to generate two different outputs, canopy height in 1 year and canopy height in the other year. And then Isaac will show some of the tools we have to help you compare and do difference and see where those changes might have occurred in this specific area of interest. All right, that's what we're going to show you today. I'm going to start by showing out the high level, how you would kick off these workflows, and then Isaac's going to go into the detailed analysis. So let me just switch over here. So again, this is all integrated into our Wherobots Cloud infrastructure. I'll give you a quick tour of Wherobots Cloud if you haven't used it before, but this is our notebook environment where you can spin up hosted Jupyter environments along with associated compute that you can use to kick off these types of workflows, kick off these types of processing. Isaac's actually going to show you our hot off the presses brand new VS Code extension, so you can do all of that same type of processing and same type of workloads from your own VS Code experience. But also within Wherobots Cloud, if you've signed up for the private preview of RasterFlow, you'll have access to our model hub. That's where we have pre-populated listings for the models that we support today. You also see here over time models that if you bring your own models to the platform, you'll have listings for the models that you've brought and ability to share those across your organization. But each of the models, here's the one we're going to run today, the Canopy height model. Some details about its origins, what it was trained on, the associated research paper that was published, so you can learn the ins and outs of this model, where you can find sample outputs to see what this model actually produces, details around what data it was trained on, and therefore what we would recommend you run as an equivalent input data set so you can get good output results. Each of these models then also has an associated solution notebook. So you can just click on this link to spin up a notebook environment where you can run that model with a few lines of code and try it out for yourself. I'm going to switch over now. This is a notebook environment I set up earlier to actually run this model. Again, this is our hosted environment. We're hosting Jupyter notebooks along with associated compute, so you can run it directly in our environment. And Isaac will show how you can do this, also do this in your own VS Code. But this is a solution notebook we have, just outlining what we're going to do here with this Canopy height model, how we're going to run it against the high resolution imagery provided by the NAIP program. But to actually run it is relatively straightforward. Similar to the last example we ran through, it's just a matter of choosing your area of interest. That could be a GeoParquet, that could be a GeoJSON file that you might have indicating the boundary of the area you'd like to work with. In this case, we're using a library maintained by members of our team called the Well-Known Location Services. Library uses Overture data. So if you have any places or admin boundaries in Overture and you want to use those as a quick way to get started with an admin boundary, you can do that with just a few lines of code. So with this notation, I'm referencing a specific town in New Hampshire called Nashua, and I can quickly get a GeoJSON representation of that admin boundary, and then I'm going to use that as the AOI input. I should also know this, in this case, we're running it against a single AOI. We also have options where you could run multiple AOIs in a single workflow. So if you have more of a sparse mosaic, maybe you have drone captures from many different regions, you want to run all that together in a single workload, that's also supported. You can pack together those AOIs in a data frame and feed those in one time as a workflow. But once we have the AOI, we initialize our RasterFlow client. And we're going to, as I mentioned, for that AOI, we're going to run for two different time periods to get two different versions of the outputs for 2021 and 2018. And then we're going to compare those. But running each one is as simple as these lines of code here. So we're calling our pre-built recipes. So these are our highest level APIs that bundle and orchestrate all of those steps of the workflow together into a single call. All it takes is the AOI that I defined above, the time range. So in this case, I'm grabbing 2021 imagery. So I'm specifying a time range between 2021 and the beginning of 2022. I can specify an optional CRS if I want to reproject the outputs of this model. And then I specify the model itself. So in this case, I'm referencing that CHM, the kind of Canopy height model provided by Meta as the specific recipe I want to run. And that's it. That kicks off a workflow that will run to do all that processing, grab the imagery, do the mosaic creation, run the inference, and generate those outputs. I'm running, this was previously run, so this time it was hitting cached results, only ran in 8 seconds. Typically, this might take, for a given AOI, might take 10 to 20 minutes to complete all of those steps. Yeah, but that's what it looks like to kick things off. I'm going to switch over now to Isaac, and he can show you how you then can do some more analysis once you've get the results of those outputs.
Hey everyone, let me just share my screen. Cool. So as Phil kind of walked you through the actual notebook experience, we had kind of built this before a lot of the agents started getting very good and they started getting integrated into like IDEs and whatnot. And so, for me personally, I really enjoy like writing code in VS Code because I have my Copilot chat, I have all my extensions and whatnot. And so, today I'm going to kind of show you the new Wherobots MCP and extension. And it's actually very simple to set up. So I have VS Code running here. I basically, all I have to do is go to the extensions. And if you just do a search for Wherobots, you'll actually really quickly find the only extension is our main one where you can click install. And then from there, all you have to do is once you're in Wherobots Cloud, you can go to your settings. And then if you scroll down to API keys, you can create a new key. And then once you do that, you just copy it. And then what you can do is you hit Command Shift P and then just search Wherobots. And then there's a set API key button here. You just copy paste that in and you're good to go. So essentially what that does is once you install and set that up, you have a Wherobots little icon here in the side pane. You can actually see that you have once you've kicked off like an active notebook. The zonal GeoID notebook I have running here, it's a tiny. You can actually see it here and connect to it. And then you click the little connect button. And essentially what you do is you can open up a notebook. So I'm opening up the same canopy height map notebook that Phil was running for the deforestation change. And if you go up here, you can actually collect or connect to the kernel. So you hit Wherobots, and then you can pick the zonal GeoID one. I've already connected it here, but essentially from here, I have access to the Spark cluster that's running in the cloud. I have access to all of the, the RasterFlow notebooks. I can start running code directly from my notebook. I can start interfacing with Copilot Chat or Claude or Codex or whatever you're using. And so kind of running through, I have some pre-computed outputs here that I already ran, but I have some outputs from the 2018 Canopy height run and then the 2021. And essentially all I'm doing here is I plot, it takes about 30 seconds to download that data and plot. It's a ZAR file. And essentially the higher canopy height is this is all in meters. So the brighter values are going to be higher canopy. Then the darker, more purple values will be less canopy height. And I'm showing this for that was 2021, so this is 2018. But I really want to do some analysis, like what does the growth look like? What tree loss has happened over this 3-year period? And so very easily, I'm just since it's ZAR, we're in X-ray land. We can just quickly compute the difference of that change in meters. And then I can actually clip the negative change. So anything that was actually a loss of tree canopy height, I can actually plot that as well. And so you can see here, darker values are going to be less change. Very bright values will be more change. And then you can kind of hover over and see the actual change in the value. I can do the same for growth. So I can clip to positive values only and actually plot that so you can see darker green values are increase in canopy height. And then what's also interesting is I can actually essentially threshold. So like, let's say I want to convert this to polygons and then join with some other type of data like NDVI or try to understand some other variables that I have. So what I'm doing here is I'm essentially creating a binary mask of any canopy height loss that is greater than 20 meters. And then I'm converting these to polygons just using raster features shapes, putting that in a GeoPandas data frame, and then connecting any touching polygons. And so now I have some pockets, about 9,000 pockets of this deforestation that was greater than 20 meters. And then once I plot that with a base map, I can essentially see in red, these are the actual polygon geometries. And if we actually zoom in here, you can start to see that this kind of, it seems like it makes sense, right? So like this area seems to have been cleared out over that 3-year period. You can zoom in on other areas. This area seems to have been cleared out in this period. And then once you have it all in geometries, you can do some post-processing, you can compute some area, and let's go ahead and do that. So what I'm going to do here is I'm going to create a new cell, and I'm basically going to copy in this, like, I'm going to use Claude Sonnet here with Copilot Chat, and I'm just going to hit go, and I'm going to let it see. We're going to see what it does. Hopefully it doesn't fail on me and embarrasses me, but you know, let's go Sonnet. Let's see what happens. So I basically just queried it to say, hey, I want to compute like the average area of these deforestation polygons. Like what is the average area in hectares of this deforestation? And so essentially what it's going to do is it's going to write the code for me directly. And bam, I have a new cell of code. I can run it. And now we have deforestation. Actually, it seems like it broke. Let me try again. Let's see. Okay, we're live debugging this right now. We're going live. But yeah, essentially this is kind of the workflow that we're trying to experience, is that instead of having to do the cloud notebooks, we can essentially have everything here, start communicating with Copilot and Claude Code or whatnot, and start doing all of our analysis where it has access directly to our Spark cluster. So we'll just say, come on, Sonnet, let's try again.
I don't know if you saw that note. The kernel already had those variables. I don't know if it was trying to reuse a previous
Yeah,
value.
I already had computed it. I just deleted it. Let's try it again. Actually, let me rerun this. We'll just recompute this change. How about that? Cool. Okay, we're gonna rerun. Should only take a second or two. Yeah, and then let's run this. See, there we go. Boom. I just had to rerun. Cool. So on average, we have about 9,000 polygons of deforestation. A lot of them are quite small, so they might be worth cleaning up or filtering. But essentially, we have computed the average area in meters squared, in hectares, and kilometers squared. And we can basically just think about extending this to any of your analyses. Whenever we run RasterFlow jobs, it outputs into a managed S3 bucket that you can access. And then you can continue doing any of your analyses. You can transfer that data outside of your bucket into other buckets. You can also, I didn't show this here, but essentially what we want to do is GeoPandas isn't really scalable, but since you already have access to your Spark cluster, you can read these geometries, this GeoPandas geodata frame right back into Sedona and start doing some larger scale analyses on the cluster that in a distributed manner, you can convert these geometries to PM tiles so you can then go visualize it. You can just, the world is your oyster. You can do anything. But yeah, that's all I have to show.
Awesome. Thank you, Isaac. Phil, do you want to, we've got some more things about sort of roadmap of RasterFlow. You want me to go over to that for a second?
Yeah, let's cover that. Yeah. Do you have that slide handy or?
You got it.
Okay, cool. Yeah, so just a couple preview of things that are coming up here for RasterFlow. So we're going to be building out the models that we support as part of the private preview. Next on our list, a couple areas we're excited about. First is we're doing a lot in the embedding space and working with foundational models. So we're seeing a lot of interest from research teams that hear about the potential of these foundation models and how they could be, a single data set or a single model that could potentially work for a large variety of different Earth observation use cases. But they really want to try it out and see where it works, where if it does work for their use case, could it simplify their pipelines? And so for right now, our goal is to help people simply generate these embeddings at scale for their chosen AOI and their chosen time range. With that in mind, we're really targeting two initial models to support it to start, starting with OmniEarth coming out of the Allen Institute for AI. And shortly after that, we'll be supporting Tera model coming out of the University of Cambridge. So you'll be able to, similar to the workflows we just showed, where there'll be high-level recipes or high-level workflows you can do to run like Canopy height model. These will be built in as additional models that you can run to generate these embeddings, right? These are going to be multi-dimensional vectors per patch or per pixel that represent some signal about what that pixel or that patch represents. And we'll be able to generate that at scale. And then you can use that for use cases like similarity search to find other areas that are in the world that are similar, look for change, a variety of different use cases that you can support once you've been able to generate those embeddings. So stay tuned for more on that. We'll be talking more about that in upcoming webinars, upcoming blogs with some examples too about not just the generation of those, but the use cases, what you can actually do with those embeddings once you've generated them. But we're also excited about this other model coming, also another model coming from Meta called SAM3. So this is their segment anything model. Basically, it's been trained on all sorts of imagery, including satellite and aerial imagery, and is a general purpose model for any type of segmentation, detection of, and we can use it then for object detection, for instance, for a variety of use cases. So this is currently in testing, and we hope to be announcing this later or releasing this later this month. You see an initial run. This is for that same area in Nashua, and we just fed in as a prompt to SAM3. Let's look for all of these objects. There's a longer list you probably can't see in that screenshot of different types of objects we're looking for, from solar panels to golf courses to airports to airplanes, roofs. I just have highlighted a couple here. The pink are all the roofs that it's found in this one specific AOI. And if you can just make out, I also asked it to look for airplanes. So there is an airport there, and it did highlight in white the airplane sitting parked there along the runway. So initial indications are, this model works reasonably well for a wide variety of different use cases, things people might want to find in the physical world. It may not be the best performing model when you really want to optimize a model for plane detection or roof detection or solar panel detection. There are going to be better models out there, but as a quick model that you can use to try out, see if there's potential for using these types of models for your specific use case, we think it's going to be a great first model for people to try out, and we're excited to bring that to the platform here shortly.
There's a question from Jordan in the chat in the Q&A that I just want to we can maybe jump into now. By the way, if anybody else has questions or things that they want to cover, we're happy to do so. We're kind of getting towards the end of the presentation here. I got a couple more slides, but the question from Jordan is, are you able to elaborate a little on how RasterFlow works under the hood? For example, how do the image composites work, image batching, processing batches into models, etc.? Is all this powered by Sedona? So the answer is no. RasterFlow is, and Isaac, I'm sure you're going to elaborate here, or Phil. RasterFlow is an independent engine. So we now actually have two engines within Wherobots. We have our WherobotsDB engine, which is our highly optimized and compute efficient version of Apache Sedona that has additional functionality beyond just the open source, a significant amount of functionality beyond the open source within it. So that's really what you're using for doing like vector to raster conversions or polygonizing things. There's a number of different, over I think 100 functions for raster processing, RS functions. But RasterFlow is a completely different engine. So Isaac, maybe if you want to go into how RasterFlow is different than WherobotsDB.
Yeah, so I think one of the big things that we do with RasterFlow different than Sedona and WherobotsDB is that we're using a Kubernetes cluster that runs Ray data. Essentially, we found that this handles like array land and raster data a bit more performant, and so it has a bunch of like secret sauce and a bunch of optimizations that we've done, including like CUDA streaming and whatnot for model inference, building these mosaics. We are doing image composites, so we're pretty flexible on, do you want the average, median composite over a year? Do you just want the raw data mosaiced and, imputed for like cloud or no data pixels? So we're trying to remove all of that processing and that infrastructure for users who just want to get from point A to point B and do their analyses. Where essentially you feed in this time range, you feed in this date, and you say, I want to run Fields of the World, I want to run this Canopy height model, or I have my own UNet or segmentation model, and I just want to run on this time range in this AOI. and then give me the output ZAR or COG or polygons so I can then do my analytics. So really it's more about removing that barrier, making it like the ease of use better. But we also do have a bunch of performance optimizations, like we use Torch AOT inductor compiled and exported models, so we get high performance PyTorch. We're doing async, CPU CUDA transfers so that we're not actually bottlenecked waiting on CPU. We're using ZAR v3 sharding and chunking to make sure that all of our data transfer in Zarland is incredibly fast. A lot of RAID data optimizations, just so that the users don't have to think about that because we've already done all the legwork for that.
Cool. And then Jordan has a follow-up, and maybe you already started to address some of this, but separately, there's a lot of work going on the wider Pangeo community regarding GPU native raster processing, i.e. or e.g. decoding and I/O. Is RasterFlow doing similar work?
Yeah. So I think it's following similar structure, but ours is actually built and battle tested and performance is quite good. We have performance benchmarks. So yeah, we're using a lot of Pangeo like community tools. So yeah, definitely look at those tooling, and you might think of this as like a more optimized version of that's already deployed.
Yeah, exactly. I mean, the whole point of this is that instead of you taking, the effort to build all these individual elements and test them and make sure that they're optimized, we've taken care of that for you. And to Isaac's point, we will be coming out with some benchmarks. We've done them internally, but kind of communicating how this performs relative to the other options that are out there in the very near future, in the next few weeks, I believe. All right, so one other question here, and maybe this, Phil, would be a good one for you. So Ushari Mandala asks, does the Meta SAM3 model work with Sentinel-2 imagery? What's the lowest spatial resolution at which it can reliably detect objects?
Yeah, great question. So generally, yes, SAM3 is built as a general purpose model that can work independent of imagery. Doesn't necessarily impose any strict requirements on the resolution of the input imagery. But having said that, if you compare Sentinel-2 with, per pixel representing 10 meters, and the NAIP imagery, in this case, we're using a specific NAIP data set that is where each pixel represents 60 centimeters. The types of objects you're going to be able to detect are going to be very different. So Sentinel-2, you will not be able to use it to detect smaller scale items like airplanes or roofs, except for maybe potentially much larger roofs on more industrial buildings. So that we're going to do more testing on that, but generally it should work. It's just with that limited resolution of Sentinel-2, you're going to be limited to the types of objects you can represent. Again, think of objects that are going to be tens of meters wide in any dimension. You're going to need objects of that size that you can then reliably detect with SAM3.
Cool. And I know, Isaac, you've done some testing of potentially some super sampling models. I know that we're looking at potentially bringing those on in the future. But have you tried SAM3 with any of those super sampled outputs? I'm just curious.
I have. So we are onboarding a Sentinel super resolution model, the Sen2SR model that upsamples to 2.5 meter from 10 meter Sentinel-2. And it does seem to perform better than just the raw 10 meter outputs. And so I think mostly around like getting the boundaries less pixelated around certain objects. But yeah, I think for me, in my opinion, like SAM3 is quite good on NAIP, just because it's already a higher resolution. But it really just depends on what you're trying to detect, right? So like you can't really see certain objects at 10 meter or even 2.5 meter very well. But SAM3 is quite good because it's trained on a bunch of aerial imagery that's high res and very dense images. So you can expect it to do well for a lot of these dense objects, but maybe not as well for rare objects that it hasn't seen in its training data distribution.
Yeah, makes sense. Cool. All right. Well, I'll kind of close out. So, before we wrap up, I know we've talked a lot. Today has really been focused on on RasterFlow, which to the previous question, RasterFlow is an independent engine that's built specifically for computer vision and Earth intelligence. Um, but I do want to draw attention to WherobotsDB as well. Obviously, Isaac was using some WherobotsDB functions in his demo, which sits all within the same sort of coding experience and user experience. Um, and we actually just released a new version of WherobotsDB today. It's now getting GA, our version, like next version of WherobotsDB, which is a even more performant and more efficient than the previous iteration of it. We've built a number of different enhancements into it. Um, but with that, what we shared and what we're continuing to share is, just the breadth of functions for these are using our spatial bench, which was part of the Apache Sedona project that we rolled out this past fall. We continue to benchmark how well it performs relative to other Spark-based or distributed computing engines. And so this gives you a sense of like the overall capability for especially larger spatial joins, heavy joins, geometry constructions, distance joins, multi-way joins, KNNs, et cetera. And many times, especially at the very large scale, these types of operations don't finish on other spatial engines. So it just gives you a sense for what you can expect when you're working with WherobotsDB. And we're continuing to push in more sort of price performance to it so you get the most efficient results possible. But it doesn't just stop with vector operations. WherobotsDB is also really enhanced with additional raster functionality that is not available elsewhere, including in our open source Apache Sedona. So that includes our OutDB raster support, which enables you to reference the metadata associated with your rasters and then federate them out into your node of your cluster without reading those rasters into memory, which is a really critical thing for distributed computing for raster data. It makes it so that you're able to handle a much larger extent of raster imagery, doing things like raster algebra, map operations, classification or value mapping, resampling, CRS reprojection at a much larger scale without worrying about bogging down your IO with that imagery. And then, of course, you also have raster to vector interoperability, zonal statistics, raster clipping, masking, and filtering, and then joining raster-derived features with vector and tabular data using Spark SQL. So a lot of those capabilities are all additive to everything that you're getting with RasterFlow. A couple different customer examples before we wrap up. So one, Satcher has been a customer with us for quite a while now, working out of India. And so they've been really kind of excited about the pipelines that we've been pushing into production with them. And they're definitely actively working towards rolling out some of this RasterFlow capabilities as well. But they're both kind of updating their own base maps and merging heterogeneous vector layers, and then operationalizing raster processing within those. So we're just excited to see what they're doing to productionize their data workloads with Wherobots across various different scenarios. And then additionally, Leaf Agriculture. So Leaf's been a customer for over a year, and they just rolled out their new Leaf Lake offering. And what's really neat about that is they're taking data from telemetry from vehicles, tractors in particular, across millions of acres, and then feeding that into individual not parcels but field boundaries for each of their different customers, so that those customers can then predict and understand yield, their seed rate, their crop that they're working with, and better use that to plan and organize their harvest sort of process. So I actually need to have a couple of different webinars with each one of those customers in the future, but it's some good examples of, you know, how folks are doing both vector and raster operations with Wherobots. Cool. If there's any other questions, I'm happy to address them. Let me just see one more. Is there more Q&A? Might have covered this already. So thanks again, Jordan. Might have this covered already with regards to cloud availability. Is Wherobots AWS only, and can Wherobots cluster be located in a specific region, UK South, Europe, London? So currently, to answer your question, Jordan, yes, Wherobots is primarily available on AWS regions. If you have a unique deployment option, we're happy to cover that with you. We do have the ability to deploy our Spark-based engine and other cloud services as well. So we can talk to you about that. Depends on what your use case is exactly. And then in terms of regional availability, yes, the short answer is we can absolutely deploy. And we do have multiple different regions already available within AWS, and it's very easy for us to deploy a new region as long as we have a clear signal that it's going to be utilized on an ongoing basis. So right now we have US East, US West, EU West out of Ireland, India, and I believe we're looking at doing Australia, one of the regions in Australia, or maybe the main region in Australia, I'm not sure, in very short future based on customer requests. So again, happy to work with you on that. Just let us know. Cool. All right. If you are interested in getting started and trying out Wherobots, definitely go to our website, go to wherobots.com. You can get started there. We are available on the AWS Marketplace for our professional edition. And we also just rolled out an integrated payment option natively within our cloud service as well. So you can, if you don't want to upgrade via and use our Pro Edition via Marketplace, you can also upgrade via just credit card. So that's an easy option for you now. We've integrated Stripe payments to enable you to do that. And then also you can, of course, try out and use the Spatial AI coding assistant on VS Code. So it's now sort of fully available. It's available even with our community edition. I verified that yesterday. So you can try it for free. You can play around with it as much as you like. You can see how it can help you develop and build things in Wherobots. It will sort of interrogate what's in your catalog, including what's in the open catalog that we have available for you, or things that you bring in via S3 connection or just upload directly. Those are all sort of things that will interrogate and make available and help you, develop with quickly. All right, I think that is everything we had. I'll stop sharing. Any final thoughts, Phil or Isaac?
I know, just stay tuned. We'll be rolling out. I plan to do these once a month with more developments on the SAM3 front, embedding front. So stay tuned for more announcements and webinars for RasterFlow.
Yeah, when do we expect, what is going to happen next there, Isaac? Are we going to have the SAM3 next, or is it the embeddings models next?
Probably embeddings models, but maybe SAM3 can also be next. Who's to say? Yeah.
Okay.
Well, whatever new stuff is coming, we'll have it every month.
Yeah, exactly. We're going to keep doing this. Very cool. Awesome. All right. Well, thanks for all the questions and follow-up. We really appreciate it. And feel free to reach out to us. We're available anytime, and we look forward to hearing from you. All right. Thanks, everybody. Have a good one.
Thanks all.